All right, here we go. Day 3 of our chapter of our final exam cheat sheet. And in this video, we're going to be covering questions 10 through 15. So we're going to attempt to get through 6 questions today. Our first question we're going to be covering is our last question from chapter 3 on graphing quadratic functions. And then the other 5 questions will all come from chapter 4. Okay, so this first question is referenced in chapter 3, section 4. In chapter 3, section 4, we talked about graphing quadratic functions in vertex form. So this different kind of organization of the quadratic is what we call vertex form. It's kind of the equivalent within linear functions of writing something in y equals mx plus b slope intercept versus standard form or line intercept, all that kind of stuff. Okay. This is just one of the arrangements of a quadratic. It's still a quadratic. It will still produce a U shape, a parabola. I know that because there's this x squared element, even though the x is trapped here inside of the parentheses. But because of the way that this is arranged, there's actually a lot of information I can pull out of it. Namely, since it is in vertex form, I'll be able to identify vertex very quickly. So let me just go ahead and jump to that solution very, very fast. So the actual vertex based on the information here is going to be as follows. Okay, so before you jump to any conclusions, because there are probably some different ways that people will interpret this, let me break down where these come from. First off, this -2 does not come from this first element. This first piece here that's multiplied out in front with any quadratic function simply will dictate the shape of that parabola, namely how steep that parabola is, whether it's happy face or sad face. Okay, this is not where that -2 comes from. This -2 and 3 come from these 2 elements. You may be thinking like, okay, I get the 3, but why is it -2 and not this +2? Okay, here's why. This x value within the vertex form is essentially the piece of x that makes this parentheses go to 0. So if I were to plug in that -2 in for x right here, -2 plus 2 is what makes this parentheses go to 0, and that's where this comes from. Okay, so for instance, had this read like x minus 7, then my x value would be a +7. If this read x plus 3, then this would have been a -3. Okay, so kind of the simple way to attack this would be simply take the opposite of whatever sign is inside the parentheses. That's an overgeneralization because that ends up changing if there's ever something multiplied in front of the x. But again, it's this x element more specifically comes from what value will make the parentheses go to 0. The 3 is far more straightforward. That does in fact come from this element subtracted or added on the back end. Because it's +3 over here, that's why it's a +3 here. Had it been -3 on the back end, then that would have been a -3. Just be prepared for any of those situations. But vertex directly in vertex form is just as simple as looking at what values you have here and translating them into your coordinate point. Okay, so this will be the location of that extreme point. Whatever this may look like on the actual coordinate grid, this is the location of that vertex, that extreme point of that parabola. So if you recall, in problem number 9, the last problem we did in the previous video, we first went about the business of identify the axis of symmetry, which is the vertical line that will chop our parabola in half, and then used that information to fill out our vertex. In this problem, we can actually do the reverse. We simply interpret what results we have going on here into our vertex coordinate point. And now for the axis of symmetry, since the axis of symmetry has to chop our parabola directly in half, and it has to also pass through or include this vertex point, I can simply do this. Since this is a vertical parabola, and it's really all we have experience with so far, I'm going to have this equation for my axis of symmetry. X equals some number represents a vertical line. So where is that vertical line located? Well, when x equals this value, -2. And so from the perspective of how to go about graphing this quadratic function, I would identify where the axis of symmetry was. So it would be a vertical line 2 units to the left of the y-axis. And then along that axis of symmetry at -2, +3, that would be the actual location of my vertex to this parabola. Okay, so identifying these two pieces, just like in problem 9, I had to go about identifying axis of symmetry and vertex. It's just a lot faster in this case, a lot less tedious as it was for problem number 9 when we had a standard form, or ax squared plus bx plus c version of a quadratic. But now it's going to proceed pretty much as normal like it did for question number 9. So at this point, now that I've identified axis of symmetry and vertex, my next job is to fill out an XY table. How many values do I need for this XY table? 3. I need 3 coordinate points. Why just 3? Well, because of the fundamental U shape of a parabola, 1 point is not enough. 1 point's not enough to give me any information about any sort of shape. 2 points, it could be anything, including a line. But 3 points are kind of the minimum I would need to describe a U shape, okay? I can create where that U opens up and that sort of thing. So that's why we go for 3 coordinate points. But here's the good news. Just like in problem number 9, I can use the vertex that I discovered as one of the 3 coordinate points. In fact, I'll use it as my middle of the 3 coordinate points. So in this case, -2, +3 will be one of my values in my XY table. It'll be the middle one. And then my suggestion for you guys was to now pick a value for my other 2 x values, go a unit bigger and then a unit smaller. So in this case, a unit bigger than -2 could be, say, -1. A unit smaller could be like, say, -3. I usually just keep it simple and go a unit to either side. Okay. And at that point, now I will go through the process of actually plugging in both of these values into my original function. So let's write that stuff out. My original function was as follows. -2 times, and in parentheses, x plus 2. I'm going to end up replacing that x with these values. That parentheses is squared, and then +3. That's going to spit out some value, and that will end up creating a coordinate point. I'll do the same thing down here with the same exact function. It's just I'll be replacing x with a different value based on my XY table, but everything else stays the same. And so now when I substitute in this -1 and -3, I'm just replacing the x in my original function. Okay, so now I've kind of shown where I'm plugging in that value, and it's going to spit out some other amount once I go through the calculator work here. Really, all I have to be careful with at this point is order of operations. So in this case, I do have to do what's inside the parentheses first. So -1 plus 2 is going to be +1. So inside my parentheses here is a +1. That +1 squared is my next order of operations. 1 squared is 1 times 1, or just 1 again. So that element is 1. Now I do the multiplication. -2 times that 1 is still -2. And now that -2 plus 3 would spit out +1. Okay? Down here, because it's a symmetrical shape, I should end up with a 1 again. These end up should matching because these are the same distance apart from each other. Okay, so here, just confirming that math, let's walk through it. I deal with the parentheses first. -3 plus 2 gives me -1 now. A -1 squared, or -1 times -1, gets rid of the negative. Negatives cancel, and I'd be left with +1 again. That +1 times -2 gives me -2. That -2 plus 3 does, in fact, give me +1. And what I've just created are 3 coordinate points. The coordinate points -1, 1, 2, -2, 3, I pulled directly from the equation, the vertex, and the -3, +1, create enough of the shape that I can figure out what I need to. All right, so what would I do with this information? How would I use this information to help me with the next part? Because the last part of problem 9, the last part of this problem, problem number 10, you will have the option between 4 given graphs. 4 given graphs. And so you're going to see 4 different graphs of different parabolas, and your job is to identify which of those 4 represents the function that you were given. And so here's what you would do. What I would do, at least, would be to take my results from my XY table and essentially try and find which one of those sets was represented out of my options. So the first thing I would look for would be this -2, 3 vertex. So that would be left 2, up 3. So I'd be looking for a graph first with a vertex somewhere in that quadrant, in that location. And then -1, 1, -3, 1, I would know that it would give me this kind of result. Left 1, up 1, left 3, up 1. Really all that tells me is I get this. What does this information tell me? That this right here is going to be the shape of my parabola, the U shape I have. And that's why I need 3 points so that I could finish out this shape so that I know it looks something like this. And that would be enough information to choose between the 4 options you'll be given. Identify where the vertex is, and then figure out, is it opening downwards? Is it opening upwards? That's where the rest of your XY table will give you that information. And that will be problem number 10 on your final exam. Okay. That's the last problem from chapter 3. And now we're going to get into chapter 4. Chapter 4 was similar to chapter 3 in that we're still dealing with quadratics. It's just that in chapter 3, we were graphing them. In chapter 4, we're now solving quadratic equations. This first problem is going to deal with something that seems a little bit different. It's going to be dealing with properties of radicals. So for this next problem, problem number 11, you're going to be tasked with this objective. You're going to be tasked with simplifying a given radical. And it'll look similar to this. You're going to be taking a radical, a square root specifically, of a number, and then a variable raised to some exponent. You're going to be asked to simplify it. Okay, so again, just to give you a little background information, in chapter 4, we're now solving quadratic equations. And the reason why we're dealing with this first section about radicals is because ultimately when I take the square root of things, that's going to be part of how I solve for x in an x squared equation. Okay, so we kind of have to have some background information about solving these radicals. Now, in this first section, we learned properties of the radicals, similarly to what we did in chapter 2. In chapter 2, we dealt with properties of exponents, which are kind of the inverse of a radical. And there were several properties that we learned in chapter 2 regarding exponents, just like there are several properties regarding radicals. Essentially, what we're asked to do here when we're asked to simplify something like this is we're asked to basically like reduce a fraction. It's the same kind of concepts here. Basically, when I take the square root of something, I'm looking for things that are perfect squares inside of that radical. And if there are, I want to make sure I pull them out and reduce what's underneath this radical as much as possible. Okay. And so here's where I'll refer you back to a chart that we created in chapter 4, section 1. In the margins of chapter 4, section 1 notes, I had you guys basically make a list, a chart of perfect square numbers. And it's probably worth writing down again here in this. And so here's what I would do just in the margin with another color or something. 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, yada, yada, yada. I could keep going, right? What I'm creating, and most of us have these memorized in some way, shape, or form. What I'm creating at this point is a reference, right? I'm basically looking to see if, 1, is this number part of my perfect squares list? Most of us would be able to identify it pretty early on. And the answer will be no on your final exam. You will not be able to take a perfect square of this number. I could confirm that on a calculator. If I took the square root of 72, it would spit out a decimal, 8 point something. Okay. So when I'm trying to simplify this and reduce this down, my next task is, if I can't take a perfect square of this number, my next task is to figure out, do one of these perfect squares divide perfectly into this number? And there will actually be several. In this case, 4 goes into 72, 9 goes into 72. But here's what you should be doing. You should be looking for the biggest perfect square that goes into 72. In this case, you will have a different number on your final exam, but your job will be to find the largest perfect square that goes into that number. Okay, so I'll go ahead and jump right to what the solution is for the sake of time here. Okay, what I'm essentially going to be doing is I'm going to be breaking up what's underneath this radical into some pieces. Okay, just rewriting it. It's not going to be changing in value at all, but I'll jump to what's the biggest perfect square that can go into 72. Maybe some of you knew this, but the biggest perfect square that goes into 72 is 36. In fact, 36 times 2 equals 72. Got a little crooked there. Okay, 36 times 2 is 72. So this is no different than that. But the reason why we break it up here is because I will ultimately be able to take the square root of this guy and thus pull out a representative out from underneath that radical. Okay, so again, if I can find the largest perfect square that goes into this number, then I only have to do this step once. Had I gone with a smaller value, I'd have to do this multiple times. Just like reducing a fraction, if I didn't choose the greatest common factor, I'd have to keep doing the steps over and over again until it was fully reduced. Okay, so finding the biggest one will keep the work minimal. All right, but now what about the variable? Okay, my goal here is to figure out how many perfect pairs of m's go into this 5. And what you would find is that in this case, I'd be able to pull out a couple pairs of m's, right? So basically I can rewrite this as m squared times m squared, and then there'd be one extra m. This kind of refers back to our properties of exponents, that if I were to multiply these three guys back together, m squared times m, I'd get right back to m to the 5th. So again, I want to emphasize that this is just a much longer sentence version of this guy, and it's done with purpose because what I'm looking for are perfect square elements. I can take the square root of both of these guys. The square root of m squared is just m, and I'm going to have 2 of them. So that when I pull out these representatives, okay, for instance, each of these pink elements I can take a perfect square of. The square root of 36 is, in fact, 6. The square root of m squared is m. And then the square root of this m squared is also m. But notice that when I have m times m, I can actually rewrite that as just m squared. So there were 2 pairs of m's that could go into m to the 5th. I'll break that down in a second. But lastly, what I would do is there is stuff that's left over underneath the radical, namely this 2. I can't take the square of 2, and there are no other perfect squares that go into it. And the same thing with this m. There's just one more m. I can't take a perfect square of m, a single variable. And so this would be my final simplified answer. All right, so another kind of shortcut way to attack the variable aspect here. Simply put, what you could do is you could just take this exponent, whatever's underneath it, and divide it by 2. So 5 divided by 2, 2 can go into it 2 whole times. That's actually where this exponent comes from. The fact that 2 can go into 5 2 whole times, and then there's 1 m left over. So for instance, had it been like m to the 17th, all right, 2 would go into 17 8 whole times, and so that would have been the exponent there. And in that case, you would, again, have a single m left over. All right, so that's like a shortcut way you can deal with the variable. But okay, that's number 11 on our final exam. All right, let's keep going. All right, our next problem is going to be found in Chapter 4, Section 6. This is problem number 12. Problem number 12 on our final exam. And for this problem, you're going to be tasked with simplifying something. Now, in Section 6 of Chapter 4, we introduce the concept of complex numbers, the letter I, the imaginary number. Okay, and so here is where we're going to start seeing some of that stuff. This won't be terribly difficult, though. You're going to be subtracting 2 complex numbers. If you're taking notes in like a margin or something like that, essentially this is just going to break down to a combination of like terms. In fact, this is actually going to be no different a strategy than what we did in Chapter 2 when we were subtracting polynomials. Okay, basically the numbers can only combine with other numbers. The letters can only combine with other common letters. Okay, the thing I have to be careful about here, the trickiest part of this problem, is the fact that I'm subtracting a bunch of stuff, right? Namely, I'm subtracting a parentheses. So just like we did in Chapter 2, I'm going to go through the step of distributing this minus sign throughout. Now, since there's nothing multiplied out in front here, the first parentheses, that will stay exactly the same. That's still 9 plus 3i. Okay, but now when I subtract -2, If I subtract a negative, that's the same thing as adding, so that turns into plus 2. And then when I subtract this negative 7i, that again will flip that sign into plus 7i. Important first step here, arguably the step that confuses and messes up the most students. Okay, take the time to distribute in that negative. It's no different actually than what happened in the chapter 2 problem when I was subtracting polynomials. And again, had one of these been like plus, for instance, then it would have been minus a plus, and that stays minus in that case. One way to think about it is it just ends up flipping both of those signs, whatever those signs have been. And at this point, it's just a combination of like terms. The positive 9 will combine with the positive 2. That will give me positive 11. The positive 3i will combine with the positive 7i. That will give me positive 10i. These cannot combine any further. Just to point this out, I is not some variable, some unknown. I actually does have a specific value. And that value is going to come in very important for the next problem. But for right now, this is as simplified as it gets. There is problem number 12 on our final exam. Again, on complex numbers. Simple enough. Let's keep going. This next problem will also be from chapter 4, section 6 on complex numbers, but now you're going to be asked to find the product or to multiply complex numbers together. Okay, so again, the term product is the fancy math word for answer to a multiplication problem. And then you're going to be given two complex numbers to multiply together, such as these. And for all intents and purposes, the strategy that we're going to use here is not going to be very different from, again, what happened in chapter 2 when I was multiplying polynomials. Okay, I'm still going to be taking each of these objects in this first parentheses and multiplying them throughout or distributing through the next parentheses. That's still going to happen. But here's where I'm going to say it's worth taking a note here in the margin, that it's worth emphasizing again that in this section we learned that I is not some unknown. It's not some variable. It actually has a value. In particular, I equals the square root of -1. This represents the imaginary numbers. Basically, if ever I had to take the square root of a negative number, if I were to try that in a calculator, it would spit out error messages. So the way I consolidate that is dealing with the fact that I has this negative square root value. Okay, or square root of a negative value. All right, and the reason I bring that up is because that's going to come into play when I finish distributing this multiplication. You'll see why in just a minute. So let's go ahead and do the distribution process right here, which is again no different than what we did in chapter 2. So just like in our chapter 2 strategy, I'll use blue to represent multiplying 5 throughout this parentheses, and then for this positive 6i, I'll use pink because again we'll be multiplying throughout this parentheses. So nothing's really changing here from the chapter 2 strategy, at least to begin with. So positive 5 times -4 gives me -20. That same positive 5 times a positive 7i gives me positive 35i. Now I'm done with my 5 object here. Moving down the line in that polynomial, now I have positive 6i times -4. That will give me -24i. And lastly, positive 6i times the positive 7i gives me plus 42i squared. Now here is where this little piece of information is going to come into play. This I squared element will actually have a real value. It's not a variable. And this is where the curveball of the problem and the thing to be aware of moving forward. Okay? Because if I equals the square root of -1, that means if I were to take that same I and say square it, and therefore square the square root, I squared is the one and only value that if I were to square it, spits out a negative answer. I squared is actually the real answer of -1. Why does that matter? Because this I squared actually equals -1. So let me take the time to represent that here. So -20 and plus 35i, nothing's really changing there. Even this -24i right here, there's nothing really unique or different about that. I will be combining like terms just as normal in just a moment. But now when I have this positive 42 times I squared, it's worth noting that this I squared is in fact -1. And so what will end up happening is this I squared, or -1, times whatever value here is going to end up changing that sign. And so in this case, a positive 42 becomes -42. And it's also worth noting that had this been -42I squared, that would be a -42 times, again, this is -1. And so that would have turned it positive. Again, simply put, it's going to end up changing this sign. Why was that important to do? Because now when it comes to combination of like terms, this -42 is going to combine with this -20 out here in front. So that when I combine like terms, -20 plus -42 gives me -62. And this 35I and -24I, when I combine them, gives me +11I. Again, those two can't combine any further, and that will be my final result. And that is problem number 13 on our final exam. Okay, again, the one curveball to be aware of on that problem, I squared actually equals something. Just be aware of that for this little element. This will happen on your final exam. Okay, let's move on. All right, so our next problem, we're actually going to regress a little bit. We're going to backtrack a little bit earlier into chapter 4. This will come from chapter 4, section 3. Chapter 4, section 3. This is problem number 14 on our final exam. You're going to be asked to do the following. You're going to be asked to solve, but not just solve. You're going to be asked to solve using exact solutions. Emphasis on exact. Why do I emphasize exact? The exact here is going to be important because that means I'm not going to be able to use a calculator and use decimals in any way, shape, or form. There will be some problems on your final where you will be allowed to do that, and just pay attention to how many decimal places you're rounding to. But for exact solutions, I have to make sure I keep following that, and I'll point out when that takes place in this problem. So here's what you're going to see that's representative from chapter 4, section 3. Okay, here we're given the following. X squared plus 5 equals 17. And you're going to be asked to solve this using exact solutions. So a couple things to point out here. Why is this different than what we did in chapter 3 where we had to graph it and stuff? In chapter 3, the reason why we have graphs is because there are two variables. There's an X and a Y, even if that Y is represented by f of X or whatever. In this case, since it's just X, that means I fundamentally will be able to get this X by itself and thus solve for it. Okay. Now, the other thing that's worth noting here is that there's no single X term in here. I have an X squared, but there's no single X term here. That's important because that means I can apply the strategies that were used in section 3. Section 3 had to do with solving quadratic equations, and this is definitely a quadratic equation because of the X squared here. But it had to do with solving quadratic equations using square roots. And the strategy ultimately is this, that as long as there are no other X's here that can distract me from getting X by itself, what I can do here is I can get X squared isolated and then get rid of the squared by doing a square root. So we're going to start by doing an inverse operation and moving this 5 to the other side of the equation, and do that here by doing the opposite of the addition, which is subtraction. And if I subtract that 5 from both sides, I get to this result. X squared equals 17 minus 5, or 12. Okay, so I have gotten this X squared isolated. So what can I do with that result? Let me keep this going down here. There we go. So now that I've got X squared isolated, what I should be able to do to get rid of this squared element is simply take the square root of both sides. And when I do that, I get the following. Square root of 12. But please pay attention to this piece. This is what we learned in chapter 4 when it came to radicals. Anytime I take the square root of both sides, I have to include this. This plus or minus element is important because whatever the square root of 12 is, okay, it's important to represent both the positive and negative versions of that, because this will end up being 3 point something. And if I have the positive 3 point something times the positive 3 point something of itself, I get back to 12. That's easy enough to understand. Why do I need the negative? Because if it was negative 3 point something times another, or times itself being another negative 3 point something. The negatives end up canceling, and I get back to the positive 12 that's represented there. That's why I need to represent the two possible solutions. Okay, so back to what the instruction said about using exact solutions. At this point, in order to use exact solutions, I just need to simplify or reduce this radical. This is no different than what we did for the section 1, chapter 4, section 1 problem, where if I can't take the perfect square of this number, and you won't be able to, okay, perfect square of 12 is a decimal, it's 3 point something. But now I need to check, does a perfect square number go into 12? And the answer is yes. 4 goes into 12, and that's important because I can now take the square root of 4. So let me show you that real quick. I can break up this 12 into two pieces where it's 4 times 3. That's important because just like what we did in the 4.1 problem, I can pull out the representative of that square root of 4, which in this case would be 2, and what would be left under the radical would be the 3. And so this would be my final result, the exact solution to this problem. Be prepared that you will have to do a reduced radical. It'll be a one-step reduction like this, but be prepared for that on your final exam for problem number 14. All right. One more problem here from chapter 4, one more problem for today's video. You're going to be asked to do the same thing to solve using exact solutions, but this problem is going to come from 4.5. 4.5, this is number 15. Number 15 on your final exam. You will be given something like this. 4x squared minus 14x plus 10 equals 0. You're going to be given a standard form quadratic equation, ax squared plus bx plus c. It will be set equal to 0. That's important noting for what strategy we're going to ultimately use here, the strategy that we learned in 4.5, namely the quadratic formula. Okay, I know some of you guys use other strategies here. That's totally fine if you do. Just be aware that it will be kind of a complex set of numbers like this. Complex is the wrong term because that's 4.6 talk right there. But quadratic formula is the technique that I'm going to demonstrate here. In order to use that, I do need to be able to identify what A, B, and C are. A is the coefficient that's attached to x squared, so this positive 4 out in front. B is the coefficient attached to just x, so it's this negative 14 here in the middle. And C will be the one that has no x attached to it, or in this case, the positive 10. It's also worth noting that had there been anything over here, and for your final exam, there won't be, but had there been anything over here, I would first have to take that element and combine it with its corresponding like term so that it was set equal to 0, because I need that to be the case in order to use quadratic formula. Okay, so at this point, I'm going to make note of the fact that I'll go ahead and write the quadratic formula here. It should be in your chapter 4.5 notes, but as long as you have it written down in your cheat sheet and or your notes, you will not have to memorize it. Take advantage of that. So here's your quadratic formula. This is what we'll ultimately be plugging A, B, and C into. So I'll go ahead and skip directly to that. I usually go through the process of writing in the minus signs just in case I ever come across like the double negatives and stuff. But I'll just take a step to show the substitution. B is this negative 14. Yes, I do take the time to write the two minus signs for myself, just so I don't lose track of them. Plus or minus the square root of this massive mess. Okay, B squared is going to be this negative 14 times itself. And then I'm going to be subtracting 4 times A times C. A is that positive 4 out front. C is that positive 10 at the back. And then all of this mess is over 2 times A. A again is that positive 4 out in front. Okay, so there's the actual substitution process right there. Now let's actually go through the solution part of this substitution. Okay, so now that I'm at this point, I would say like, all right, well, a negative 14 is going to turn into a positive 14 in this case. Many of you would probably not need to make that step, but I go through it for my own sake. And then underneath my square root, negative 14 squared, the negatives will end up canceling. Okay, be aware of that. I shouldn't get a negative squared and get a negative number, but that will turn into 196. you'll be able to use a calculator. Don't feel like you have to have that memorized. And then I'll be subtracting 4 times A times C. Well, 4 times 4 is 16. That 16 times 10 is 160. Use a calculator there. Don't feel like you have to do it in your head. All of this is still over 2A. 2 times that 4 in the denominator is 8. Okay, one step closer. Again, I'd probably do a little overkill with how to go about solving these. It's worth doing to make sure you make fewer mistakes and get the partial credit points if you can. All right, so now figuring out reducing, condensing down what's underneath the radical. If I were to take the square, if I were to subtract 160 from 196, I would get 36 on the other side of that. All of that is still over 8. Now, here's what I will tell you about your final exam. What you will have underneath this radical will be a nice friendly number. The reason I say that, I can actually take the perfect square root of 36 here. So be aware of that, so that this will equal 14 plus or minus the actual square root of 36 is in fact 6. Okay, so be prepared that on your test it will be a friendly number. But in the denominator, it will be an 8. And so now I have 2 possible solutions represented here by either the plus and the minus. So when I come to my actual final answers here, I have to remember I have to keep exact solutions, no decimals. So first thing I do is this plus on top. 14 plus 6 is 20. That 20 over 8 can reduce. 20 over 8, 4 goes into both top and bottom. That would reduce to 5 over 2. That's one of my 2 solutions here. But I also have to keep track of the minus sign there, right there. So it also, or and, equals 14 minus 6, which is 8 over 8, which can reduce, this one's nice and friendly, just a positive 1. There are my 2 solutions. That is a demonstration of quadratic formula. I show a little more work than what's probably necessary for you. Just as long as I see your thought process along the way, you will get full points in that. And that will end our day 3 video. I'll go ahead and stop recording.